Alright, hello class. In this lesson we're going to be talking about continuity. There's probably not a lot new in this section. We've covered a lot of what we need to talk about. You've seen a lot of this in your algebra and pre-calculus classes. We're just sort of formalizing some known ideas here. So hopefully not a lot new here. But more just rounding out our formal discussion and definition of this topic, specifically using limits. Okay, I like to think of it as filling in previous gaps using limits, or learning the formal way to talk about continuity or continuous functions. Okay, and remember, a lot of this class is about learning these formalities, right? The formal way to talk about math, or the adult way to talk about math going forward. Okay, so like I said, not a whole lot new here. We're just going to sort of wrap things up a bit, fill in those missing knowledge gaps or notation gaps, and hopefully this one won't be too bad based on everything else we've looked at already. Okay, so here's the formal definition of continuity. Basically, a function f of x is continuous at x equals a if the limit of f of x as x goes to a is equal to f of a. Okay, so we want to move away from that old school way of thinking about it, which is like, if you remember in your pre-cal classes, you would basically just say, oh, a function's continuous if you can draw the graph without lifting your pencil, right? There are no holes or jumps in the graph. I don't particularly like that way about talking about continuity, because it's more about defining continuity in what it isn't versus what it is. Okay, what it is continuity. All right, so basically continuous at a point is just saying that the limit and the function match at x equals a. That's what continuity tells us. It's basically a property of the function value and the limit aligning with one another. In other words, continuity implies that f approaches, let's say, f of a as, let me do it this way. Let's say f approaches L as x approaches a, and f also equals L as x equals a. Okay, so what continuity is doing is basically saying that the behavior, right, of f of x matches under the limit and the equal sign, right? So that the equal sign and the limit match one another. Okay, so we're getting the same behavior as we approach a and equals a. Okay, so that's really what continuity is all about. It's about matching behavior. Okay, so let's look at a graph here and talk about sort of the different forms of discontinuities. We sort of already talked about this before, but I want to give the limit description of why it's not continuous. Okay, so to start with, let's look at here at -3. Okay, here at -3, if my function in blue here is f of x, okay, we know that this function should be discontinuous here, right, just from our previous knowledge, because there's a hole in the graph, right? But we don't want to use that terminology. Well, I mean, we can, but there's a more official way to talk about a hole, and that is that f of -3 is undefined. Right? So the function itself is undefined. However, the limit is going to be 2. Right? The limit as x goes to -3 of f of x is 2 based on the graph. Okay? And 2 does not match f of -3, which is undefined. Right? So this is no match. So this is basically what happens when you have a hole. A hole is when the limit exists, but it does not align with the function value. Okay, so so the limit exists, but it's not aligned with f at x equals 3. Okay, so that's what's happening here. Okay, now let's look at -1. -1, we know this as a jump. Okay, so here the function itself does exist there, right? So here f of -1, well, we do have a closed dot here up at 5, so f of -1 is 5. So the function actually exists there. However, it's going to be the limit that does not exist. Right, because it from the right side the limit is 5, and from the left side the limit is 3. Okay, so as I said, the limit from the left side of -1 is 3. The limit from the right side of -1 is 5. These don't match. Therefore, the limit just straight up doesn't exist. So if it doesn't exist, it can't even equal what f of -1 is. Okay, so that's what happens in a jump. A jump is when the limit does not exist. Okay, so that is the more accurate way. I mean, we could still call it a jump, but the formal way to talk about a jump is saying that the limit does not exist. Okay, next up here is a blow up. Right? And this is a case where, as we've talked about, where f of 3 is undefined because it's going to end up being a constant over 0 there. Okay, so it's specifically undefined. However, notice that the limit also doesn't exist. So the limit as x goes to 3 of f of x does not exist. Now you might think, well, aren't these the same? Don't these match now? And the answer is essentially no. If f of 3 or f of a or f of any value is undefined, your function's automatically going to be discontinuous there. Okay, so this is basically a blow-up. Right, because the limit as x goes to 3 from the left of f of x, so from the left it's positive infinity, and from the right it's negative infinity. Okay, so anytime you have a blow up, your function is going to be undefined, even if they match on both sides. We'll look at that example in another graph real quick, but yeah, essentially any sort of blow up is going to be not continuous. And finally, for this graph, this is here a removable discontinuity. So we have a hole here, but we have a closed dot here. Okay, so as I mentioned in a previous video, this is a removable discontinuity because all we've done is removed this point. That if it were here, it would be continuous, but we have moved it. Okay, so in this case, f of 5, well, we can actually get a value. F of 5, if we map this over, looks to be 1. The limit exists, right? The limit as x goes to 5, we can find down here, it seems to be, let's say it's 3, or negative 3. Okay. So here the function itself exists, the limit exists, however they don't match. All right. So this is what it looks like when both the function value and the limit exists, they just don't match. Here the limit existed but the function value did not. Okay? Here the limit did not exist but the function value did. Here neither existed, and here they both existed but did not match. Okay? So that's a removable discontinuity, is when you have both of them, right? So I'll say both exist but don't match. All right, finally, if I look at something like here, right? Let's say this is at negative 2. F is continuous as far as we can see at negative 2. Why? Well, f of negative 2 seems to be 2. Then the limit as x goes to negative 2 of f of x is 2. So these match, they're the same thing, both exist and match. Okay? So, and really at every other point, that's going to be the same thing too, because at every point, other than the few we looked at, the limit exists, the function exists, and it all matches, it all lines up. Okay? All right. And as mentioned before, for this function, let's say g of x, it's still not continuous at 0. And that's since g of 0 is undefined, even though the limit would be infinity. But remember, when a limit is infinity, that's still a does not exist. It's just one that we can use to describe the behavior. So yes, the limit is infinity. However, a function is never going to equal infinity. That's never going to happen, at least not in this class. Okay, in some of the higher level classes, you may see an infinite value in a function, but not at this level. Okay, and then here is a jump where there is no g of 1 either, right? G of 1 is also undefined. So g is not continuous there either. So notice what I've done here. I am able to tell whether a function is continuous or not based solely on whether the function is undefined. And actually, this is what the book calls the continuity checklist. And there's an order you can go through to check to see if a function is continuous. And once a function does not satisfy a certain criteria, it's not continuous there. All right, so here's the continuity checklist from the book, the way I like to write it, which is if we're checking to see if f is continuous at, say, x equals a, here's the order of best approach, because 1, is f of a defined? Right? If f of a is not defined, you can pretty much stop right there because it's not going to be continuous. 2, does the limit exist? If the limit doesn't exist, that means you have a jump or you've got blow up or something like that. If f of a is not defined, you have a hole or a removable discontinuity. Does the limit as x goes to a of f of x equal f of a, i.e. do these two match? And that's the last thing to check, because if f exists at a and the limit exists at a, then the last thing to check is, do they match at a? All three need to be satisfied for f to be continuous. Okay? All right, now since we are using limits to talk about continuity, we can actually use the whole left and right-handed limits to help us sort of expand our ideas of continuity, to talk about left and right continuities. Okay, so, and it's how you might expect. Okay, so f of x is continuous from the right at x equals a if the limit as x goes to a from the right of f of x equals f of a. And similarly, f is continuous from the left at x equals a if the limit as x goes to a from the left of f of x is equal to f of a. So, for example, if we have this function here, right, and let's say this is 1, so here's, say, f of x, this function would be continuous from the right at 1, okay, because we are coming at it and there's a closed dot. However, if this function sort of continued on over here and stopped at, say, 10 with an open dot, well, then this function is not continuous from the left at 10. Okay? So, to give an example of one that is continuous from the left, of course, you would just do this. Right? So this function I just drew, this would be continuous from the left here. Alright. Alright, now you may have noticed that unlike in pre-cal, where back in pre-cal we would usually talk about is a function continuous or not. It was usually presented that way. It's one or the other. Is it or isn't it? Here, continuity in a more formal sense is actually a point-wise property. That means it's a property of a function at a point. However, if f is continuous at every point in a set, say I, then we say that f is continuous on I. You might hear it continuous over I or continuous in I sometimes, but what we mean by this is essentially if you, if you have a graph that looks like this, right, and say this is 1 and this is 7, right, from what we can tell, right, from what we can tell, f is continuous on 0 to 7. Okay, based on what we see. However, if we look at, say, a similar example here, say instead we have some open dots. And actually, what I will do is, say we have a vertical asymptote here. Okay. So let's say this is 2, and then we have a vertical asymptote here at, let's say this is 5. Okay, not drawn to scale, of course. This function, okay, this function is continuous on, well, it's not continuous at 2, it's not continuous at 5, it doesn't seem to exist anywhere else. However, all of these other points, it does seem to exist there and be continuous. And there doesn't seem to be any more jumps or places where the limit doesn't exist. So what we would say is that this function is continuous on 2 to 5. Okay, notice how we use the open parentheses here and the closed here. We can use the closed because, well, it's going to be continuous at the, or from the left and the right. All right, so this leads us to be able to talk about so going back to our previous example here, we can actually talk about our functions on like what intervals they're continuous on. So this particular function f is continuous on the following intervals. We're assuming that this goes on forever, Okay, it may not, but from what we can see, it does. So we'll say it's continuous on negative infinity to -3. I'm going to open that up, right, because we have an open dot here, right, there's a hole. Then it's going to be continuous from -3 to 1. Sorry, -3 to -1. Okay, then it's continuous from -1 closed up to 3 open. So notice I'm not putting unions here. You may recognize that. So I'm establishing through the interval notation here that this piece of the function, it's right continuous at -1 here. So this is continuous from the right here, but it is not totally continuous at -1. Okay? Then 3 to 5, and then we're assuming 5 onwards. Okay? Okay, so a natural question is why does it really matter, right? What benefit do we get from having this more formal way of talking about continuity? And it comes from functions like this. Say our f of x is equal to, it's a piecewise function, so it's going to be x times sine of 1 over x whenever x is not equal to 0, and it's going to be 0 whenever x is equal to 0. Okay, so the reason we need this is because x sine of 1 over x, if we try to plug 0 straight into this, we'll get nothing because we have, 0 times 1 over 0 in our sign. That would be undefined, right? So thankfully we have this. So f of 0 is 0, because remember, when you plug the 0 in, that corresponds with the x equals 0 case. Okay, well now I want to know the, let's say the limit as x goes to 0 of f of x. So the reason I'm doing this, if we look at the graph of this function, okay, so here's the graph of this function using my graphing software here, and if we were to zoom in, let's zoom way in, okay, the question is, well, is this function continuous at 0? Okay, so, okay, and it appears to be. However, it's hard to use our old definition, because as I look closer and closer to 0 here, it looks like it's jumping, right? Depending on your graphing software, it looks like you have a lot of jumps happening. Okay, so it is difficult to see with the graph, and we're going to see that quite often, that it can be difficult to see what's going on with the graph, especially here where this just looks like a big smudge of stuff. It looks like this is not even a function, let alone continuous. However, right, if we want to find the limit as x goes to 0, so remember that's the limit talks about x going to 0 but not actually equal to. So that means we're going to use this piece. Now we can't just plug in the 0. This we're going to have to use the squeeze theorem. Okay, so using the squeeze theorem, I'll have, let's start with the sine piece. Sine of 1 over x, of course. We know sine of really anything is going to be trapped between -1 and 1. And so to get it to look like x, sine of 1 over x, we'll just multiply both, I keep saying both sides, all sides by x to get -x less than x sine of 1 over x less than or equal to x. And now we'll take the limit of everything. Okay, so we'll get the limit as x goes to 0 of -x. which is less than or equal to x sine of 1 over x, which is less than or equal to the limit as x goes to 0 of x. These two guys, of course, go to 0. So that implies that the limit as x goes to 0 of x sine of 1 over x is 0. Okay, so f of 0 is 0, and the limit as x goes to 0 of f of x is 0. So the answer is yes. Okay, f of x is continuous at x equals 0. Okay, even though from the graph it may be difficult to see that. Okay, so this is why we need this more formal way of talking about continuity. All right, so how I approach this here with this piecewise function is how you would approach any piecewise function if you're asked to determine the continuity of it or where it's continuous. I find that students tend to have quite a bit of trouble with this idea, so I'll go through another example quickly. All right, so let's look at this function here. Let's say f of x is equal to x squared plus 1 if x is less than or equal to 0, and 3x plus 5 if if x is greater than 0. So we want to determine if f is continuous at x equals 0. So the first thing we need to do is, well, is f of 0 defined? All right, that's the first thing in the continuity checklist. So is f of 0 defined? And the answer is, of course, in this case, yes, because we have an or equal to here. So f of 0 will go to the top piece, right, because this is when f is less than 0 or if x is equal to 0. So we'll plug it into that. It will be 0 squared plus 1, which will be 1. Okay, so yeah, f of 0 is defined. It's 1. That's always the first thing we check. Now, does the limit exist? Okay, well, there's a quick way to check that. We checked here already, this side, so that would easily be the, say, limit as x goes to 0 from the left, because this is broken into two pieces. We have x less than or equal to 0, and we have x strictly greater than 0. So let me line up the colors here. So the limit as x goes to 0 from the left side would happen here. Well, we would use this same piece. This would be the limit as x goes to 0 from the left of x squared plus 1. And we can just plug in the 0. So we get the 0 squared plus 1, which is 1. Okay, so we don't, you don't often have to write this work over and over again, but, just to show what's going on. Now, when we want to look at the limit as x goes to 0 from the right side, so that's here. This is x goes to 0 from the right. We'll use the purple piece, right? The piece when x is greater than 0. So the limit as x goes to 0 plus of f of x is going to be the limit as x goes to 0 from the right of 3x plus 5. So that'll be 3 times 0 plus 5, so we'll get 5. These don't match, so, right, there's no match. So the limit as x goes to 0 of f of x does not exist. Therefore, f is not continuous at 0. Okay? So notice what I did there. I just checked both sides. Okay? And if they match, then, and you get the same thing at x equals 0, it's going to be continuous. If they don't match, it's not going to be continuous. However, we can say that f is left continuous at 0, right? Because from the left, the limit and the function value match. Okay, so we are left continuous. But since we're not both left and right continuous, we're not totally continuous at 0. Alright, and if we take a quick look at the graph here, this is what this particular graph looks like. We're left continuous, we have a jump, and then we now start being this function when x is greater than 0. Okay, so this is pretty much how you deal with piecewise functions. Is you're basically just trying to see if the pieces match from the left and the right. Alright, so the last thing I want to talk about with regards to continuous functions is a really nice property we have about them, and it may seem kind of intuitive. That's good. And it's what's called the intermediate value theorem, also known, or what I often call the IVT. Okay, and what it says is that basically suppose f is continuous on the interval a to b closed. The closed part is really important. Okay, and L is a number between f of a and f of b. That's why it's important to be closed, because else, we need that f a, f b, and we need it to match everything. Okay. Then there exists at least one number c in a to b open, satisfying f of c equals L. So let me demonstrate what this is talking about here. So let's say I have this graph here, okay, and I know the function is continuous, and let's say here is, let's say here's A, and this is B. Okay, so f of A is here, and f of B is here. Now, let's suppose the L that I'm looking for between these two y values is here. Okay? Now, what this theorem is saying is that since f is continuous, there is no way we can get from f of b or f of a to f of b without crossing L. Okay? So that's what this is saying here, that basically since f is continuous, there's no way that we can get from here to here without crossing L at least once. So, I could maybe draw a line like this, and there we go. That would correspond with our C, right? Okay, that's not the only way, though. Right? We could instead have a graph that looks something like this, which crosses multiple times, right? But all it's saying is that there exists at least one number, C. There could be more. There could be a C1, a C2, a C3, okay, etc. So basically, there's no way we could get to f of b without crossing this line. Okay. Now, and it might be very close, right? It might be very close to one of the endpoints. So the only way we can actually get there without crossing L, right, the L line, would be if we had a jump, right? So a jump is the only way we could do that. Okay? Now, there are a lot of cool properties that come from this. One is not only is this saying that there exists this C that tells us we cross this L. We can do this for every value between f of a and f of b. So the function is going to hit every value between f of a and f of b. All right, so what do I mean by this, that f is going to attain every value? Well, if we do a similar thing here, where let's say this is my f of a, and this is our f of b, we are guaranteed to hit at least once every value between f of a and f of b. Now, we might hit more. Oops. Okay, we might hit more like we do in this case, but notice that we are hitting every y value in between f of a and f of b at least once. Now again, we might hit them more than once because we might do something like this where we're, hit them multiple times. But we are guaranteed to hit every value between f of a and f of b. That's actually a pretty cool thing. I mean, it might seem intuitive because we're talking about continuous functions and the way we know that continuous functions behave. This shouldn't be a surprise. But it is still nice to have formally. Okay, a natural question might be, well, yeah, great, this is intuitive. Why are we spending a lot of time talking about this? This comes from, or this was very helpful back before we had really strong graphing capabilities. And in fact, this is still, or can be still useful today when solving really nasty equations. All right, like for example, let's say I want to solve x ln x minus 1 equals 0. Well, using our traditional methods for solving, what you would do is say you'd move the 1 over, and you get x ln x is equal to 1. And there are a few ways you could go from here. You could divide by the x to get ln x is equal to 1 over x. And then if you did your usual equivalence here, this would tell us that x is equal to e to the 1 over x. And then what? Right? From here, the best we could do is kind of get back to where we started. Another thing we could do is at this point instead we could say that this is ln x to the x is equal to 1. Okay, but then that would tell us that x to the x is equal to e, which again leads us to the same thing we have here. So trying to do this by hand is not going to lead us anywhere. What we can do instead is use the intermediate value theorem. Okay, so the intermediate value theorem, let's just look at the interval. Let's say my interval is 0 to e. I'm just picking some values that would work nice with the natural log and whatnot. Sorry, not 0, 1. Yeah, sorry, can't plug 0 into ln. Anyway, we're going to look at this interval. So 1 to e. So I'm going to let f of x be this side of the equation here, the x ln x minus 1. Okay, so if I plug in 1, we're going to get 1 times natural log of 1 minus 1. Okay, well, natural log of 1 is 0, so this comes out to be -1. Okay, then f of e, well, that's going to be e times the natural log of e minus 1. So that's going to be 1, so this is just going to be e minus 1. All right, e minus 1, specifically, e is like 2.7 whatever, so this is positive, this is negative. Okay, so that means for this function, whatever it looks like, right, at 1 we got -1. Okay, at e we got e minus 1. Okay, so that means whatever this function looks like, right, I should say it's continuous. I mean, it is, as long as we stay away from 0. 0 is what's going to cause this to blow up, but x times ln x is continuous everywhere for x greater than 0. Okay? So, provided this function is continuous, we are going to get a solution somewhere if 0 is the L that we're looking for. Right? So by the intermediate value theorem, okay, we know there is at least one C in the interval 1 to e open where f of c equals 0. Well, if f of c equals 0, that's c ln c minus 1 equals 0. That would actually solve the equation that we started with. Now, what people used to do, okay, is they would cut this interval in half, because we don't really know where that c is, so they would cut it in half and look at, say, e halves, okay, and then see what they see. So let's clean this up a little bit, okay, and so the e minus 1 is about 1.7, and of course this is -1. So what I'm going to do is find f of e, sorry, maybe not, but I want to find the midpoint of this interval. So the midpoint is going to be e plus 1 over 2. Okay, and then we're going to plug this into f. I'm going to spare you a lot of the details here and just kind of give you the value. All right, so at e plus 1 over 2, we got about 0.15. So here, our function value is now 0.15. Okay, so here f of 1 is negative, and f of e plus 1 over 2 is 0.5. So this is definitely closer to 0. So now I know that the solution has to be in this interval. So we're going to cut it in half again and take the midpoint. So I could even take something close here, or closer, but I'm just going to take e plus 1 over 4. Sorry, once again, when you do the midpoint formula, it should be e plus 3 over 4. Again, don't get too hung up on what these numbers are. Just the idea is what I want to focus on here. So it's the next midpoint. All right, and when you plug that in, you get negative 0.48. So now we are, now we are closer than we were before, and then we will cut it in half again. So now we know that the 0 is in this, and what people used to do is just get closer and closer and closer to what that solution would be, okay, and then eventually get as close as they want, if that sounds familiar. This is sort of like you cut the interval in half and see what you get. So when you take the next continue doing this over and over and over again, and eventually you would zero in on which and go to each interval that you knew that the solution has to be in, and eventually be able to approximate the solution of this thing that you can't solve by hand. Okay, so again, don't get too hung up on the numbers here, just the idea that we can continue to zero in, get these intervals smaller and smaller and smaller to get an approximation of what or where the function is going to cross. All right, so after all that, I think that's a good place to end it here. There are a lot of neat things that the intermediate value theorem can actually prove for us. You'll see some of those in the homework, and if you have trouble with them, just feel free to ask for help, or MyLabs has a nice little help me solve feature. But I think that should probably be good enough for now, and from here we're going to start moving into the real meat of what calculus is, because you might think it's just about studying limits, but actually limits are just a tool that lead us to a more robust set of tools that are actually going to be far more useful. Well, maybe not far more useful, but they're going to be what we will focus on for the majority of this course. All right, I will see you all then. Cheers.